Okay, so how do general Hamming codes work? You can map 1 to 1, 1, 1, correct 1 error, 0 to 0, 0, 0. And this is called 3, 1 code because the code words are length 3 and the message is 1 bit. And we can map G, correct 1 error, and we have a 7-4 code. And there's also a 15-11 code and a 31-26 code, etc. So this is a class of Hamming codes. They all correct 1 error. So what do they look like? Well, G equals, we're going to start with the identity. And let's say 1, 1, 0, 0, 1, 1, 1, 0, 1, 0. Okay, let's do the case of 4, 0, 1, 0, 0, 1, 1, 1, 1, 1. So I want to say we want these to be all bit strings of length greater than or equal to 2. So how many of these are there? Of weight greater than or equal to 0. And I guess this is going to be 2 to the, this is going to be 2 to the n minus 1. Because if you add, think about this, if you add all the strings of length 1 to them, you get all binary strings, or sorry, all the strings of weight 1 to these. You get all binary strings of weight greater than or equal to 1, and we know there are 2 to the n minus 1 of them. So this is 2 to the n minus 1 minus n, because there are n binary strings of length. Okay, n is not a good number. 2 to the k minus k, and 2 to the k. So the Hamming code encodes 2 to the k minus 1, or 2 to the k minus 1 minus k bits into 2 to the k minus 1 bits. And why did we do this? All code words in row space have Hamming weight greater than or equal to 3, or all non-zero words in the row space. Why is that? Well, first, if you take one of these rows, its weight is clearly greater than or equal to 3 because there's a 1 somewhere in this identity, and these vectors all have weight at least 2. All rows weight greater than or equal to 3. Sums of 2 rows, the weight is greater than or equal to 3. Why? Because there's 2 1s in the first part. From the identity. And there's a 1 in the last piece because no two of these are equal. So if you add two of these vectors, the weight's at least 1. And sums of 3 rows, the weight is greater than root of 3 because, well, if you have a code word of weight greater than root of 3 and you encode it, the first piece of it, when you multiply by the identity, you get a weight greater than root of 3. So all code words of this code have weight greater than or equal to 3, which means it can correct one error. And that is classical Hamming code. So, yeah?
So the statement that the weight has to be greater than or equal to 3 to correct one error is valid for all linear codes?
All linear codes.
What about 3-1 code?
Yeah, the weight's greater than 3, greater than or equal to 3.
But
because
0 is mapped to 0, 0, 0.
Yeah, all non-zero code words.
Oh, right, okay.
All non-zero code words have to have weight greater than or equal to 3. So that corrects one error.